According to several published papers, there is a gap in terms of geometrical characteristics between the stochastic simulated discrete fractures network and the natural fractures network. Considering the complexity that must be faced in the building of a fractures model, this topic looks a bit academic. However, in this short discussion, we are going to argue if the stochastic simulated discrete fractures networks, DFN, is suitable to describe the geometrical characteristics of a natural fractures networks, NFN, like, for example, the natural fractures network observed in the Chiapea virtual field trip. Fractures are widespread in the rocks, and depending on their geometry, density, and aperture, might have a strong impact on the fluid flow, affecting many engineering applications like groundwater or geothermal or hydrocarbon reservoirs exploitation, as well as waste disposal management or groundwater contamination assessment. The prediction of the fracture network geometry is important, being the first issue to be faced in the complex process of building a reservoir fractures model. In fact, one piece of the puzzle is connectivity. Do the fractures form a connected path through the rocks? Especially in the initial phase of a reservoir development, when the dynamic data are not yet available, the connectivity estimation is an important study target to evaluate if the presence of fractures really makes the reservoir a potential fractured reservoir. In fact, the presence of a connected fractures path is a sine qua non condition to have a fractured reservoir. Fractures are typically organized as networks ranging from small centimetric to large multi-kilometers scales. However, while the large seismic scale discontinuities can be directly observed and modeled deterministically, the smaller events population of discontinuities below the seismic resolution is a much more elusive subject. They present generally systematic geometrical characteristics that are referred to specific stress and strain conditions associated to various tectonic contexts. It is so introduced the notion of geological fracture drivers. That means different fractures patterns related, for example, to fault or to fold or to burial stress. However, the assignment of a geological drivers to the fractures observed in the drilled wells is not straightforward because the data collected along a 1D borehole are quite poor and limited. In fact, the only data collected along the boreholes are the presence, the number, and the orientation of the fractures crossed by the well. And, in case of fractures affected by different orientations, it can be inferred also the presence of different fracture sets, each related to different stress and strain conditions. So, with the drilling of some wells, what we know is the presence of fractures, the fractures number, the fractures orientation, dip azimuth, the fractures sets. So these are the only information that we can collect from the borehole, information to be integrated with the structural context as interpreted from the seismic data and regional studies, and with the dynamic data like WTKH or interference test when available. However, to make a reliable geometrical reconstruction of a subsurface fractures network, a lot of additional unknown data for each set should be available. So, the additional data that we would like to have, but that we don't know, are the fracture's dimensions, height, and length, the fracture's shape, the fracture's terminations, the fracture's spacing, the fracture's set's timing and their interaction with the other sets, the fracture's intensity spatial distribution, that means lateral continuity versus trend or clustering. So, there are more things we don't know than we know. The lack of these data is frustrating and can lead to the building of fractures model more driven by the software rather than by geological considerations. The modeling approach generally used to describe the fracture network geometries is the stochastic simulation of Discrete Fractures Network, DFN, that should provide a statistical 3D representation. Taking as reference the Petrel subsurface software, the simulations of each set can be controlled by the following parameters: orientation, dip and dip azimuth, constant or varying in the space as driven by property 2D or 3D, density P32 or P21, constant or varying in the space as driven by property 2D or 3D, fractures dimensions, length and length-height ratio, constant or varying in the space as driven by property 2D or 3D. Actually, only point 1 is supported by real data collected in the drilled wells, while point 2 and 3 are bound to be just a geological guess inferred from different data and/or considerations. Despite the large use in many engineering applications of the stochastic simulated Discrete Fractures Network, DFN, this approach is considered by several authors inadequate because neglects some characteristics of natural fractures network, making the simulated Discrete Fractures Network, DFN, not realistic and reliable. In fact, we recognize that this modeling approach simplifies pragmatically in the absence of data some aspects. Fractures are represented by very simple shapes, being each fracture described by a single linear plane. Fracture sets are distributed stochastically in the space independently from the other sets without any consideration about timing and interaction between sets. That means that fractures of a set cross and intersect the fractures of the other sets without any constraint or relationship, as if the other sets didn't exist. Fractures terminations are always represented by I nodes, isolated, or X nodes, cross, neglecting the Y nodes, abutment, and the V nodes, link. Percolation threshold for fracture system is based in the stochastic simulated DFN on random fractures locations where all connections are fractures intersections. However, in natural systems, a significant portion of connectivity is achieved through fracture abutments or splays. As illustrated by the ternary diagram, fractures terminations in the DFN are so represented only by percentages of I nodes, isolated, and X nodes, cross, while the NFN includes also a percentage of Y nodes, abutment, and the V nodes, link. In fact, natural fractures very often branch off and extend up to terminate on other pre-existing fractures, while in the simulated DFN, the discontinuities are modeled by ideally shaped geometrical objects scattered randomly in the space. Therefore, the topology of the two fractures network is clearly different. So several authors conclude that with equivalent fracture intensity, length, and orientation, a natural fracture network, NFN, is more connected than the corresponding synthetic fracture network, DFN. Therefore, The characteristics of the stochastic simulated DFN could be misleading up to conclude that the fractures network of a reservoir is not connected, whereas the real network is well connected. These considerations rely on the studies of outcrops, mainly rock pavements, where the fracture network characteristics like branching and abutment can be observed in 2D. Pavements outcrops that are rock bed top surfaces outcropping for several meters are targeted by these studies because they contain important information that is neither accessible with vertical outcrops nor in the drilled boreholes from which we can get a skewed interpretation. The DFN limitations are evident, and different approaches based on mechanical models or multiple point statistics have been developed by several authors to generate more realistic fractures networks. These procedures include also the building of complex software to try to better represent the geological scenarios. However, the real issue to be addressed is the connectivity of the fractures network. Considering the shortage, or more often, the total lack of input data, the conceptual model, interpreted by the geologist, case by case, seems to be the fundamental guideline that cannot be delegated to any approach and software. Therefore, we wonder if alternative procedures that give more room to the geological interpretation could be utilized to try to fill the geometrical gap between discrete fracture network and natural fracture network. The idea is that the geometrical characteristics of the stochastic DFN could be calibrated using small deterministic fractures models built according to the conceptual model inferred by the geologist. Let's try to make some tests using, as reference, the fractured rock of the Chiapea virtual field trip, where we envisage to drill some wells. If lucky, some of these wells will cross fractures. The data collected along the 1D boreholes by the image log or cores would be presence of fractures characterized by different orientations, and therefore estimation of 3 sets with different dip and azimuth, O set 1, O set 2, O set 3. According to these data, we could produce a simulated stochastic DFN controlled, as per petrol subsurface software characteristics, by the following parameters: orientation, dip and dip azimuth, and concentration of each recognized set, density P32, fractures dimensions, length and elongation ratio. Being 0.2 and 3 unknowns, several geological considerations and hypotheses could be made. However, the first scenarios to be explored should be the connectivity. Does the fractures network define a continuous path? A very simple initial approach could be that of neglecting any geological estimation, considering all the fractures sets as equivalent in terms of timing, size, intensity, and concentration. Sensitivities could be performed on the unknowns parameters with the target of reaching the network connectivity threshold that is the first issue to be faced in the building of a fractures model. Is the fractures network enough continuous to represent a path affecting the flow capacity of the reservoir? To investigate this issue, we can perform iterations to estimate the minimum values of fractures length and intensity to get a continuous connected path through the rock. The connectivity index mean value of 2 has been assumed as the target of these iterations. In fact, this value describes a scenarios where each fracture is intersected by 2 other fractures in the model cells. So, we have built a small 3D model in petrol that extends per an area about corresponding to the extension of the Chiapia pavement outcrop. Considering the length of the fractures observed in the order of 1 or 2 meters, the 3D model grid has been built using cells large 2 per 2 meters and a thickness of 1 meter that is about the bedrock thickness on which we are going to focus the attention. The following initial inputs have been assumed for the iterations: a fracture's length equal to 0.5 meters, a fracture's intensity P32 equal to 0.25 square meters per cubic meter, and an elongation ratio of 1. These inputs define, in this context of cells of 4 cubic meters, 2 by 2 by 1 meter, an initial iteration scenario for each set characterized by 4 fractures, 1 square meter, spaced about half a meter in each cell. Intensity has been assumed as correlated with the fracture's length, and at each iteration, fracture's length and intensity have been increased or reduced by 5%. In fact, other parameters can impact on the definition of the connectivity. The relationship between fracture's length and fracture's intensity that defines the balance between the fracture's number and the fracture's length. The orientation concentration here assumed equal to 500 to minimize the orientation dispersion. As a matter of fact, a lower concentration would increase the fracture's dispersion and their intersections, so the connectivity index value of 2 would be reached for lower values of fracture's length and intensity. The elongation ratio, length, height, generally estimated by far larger than 1, but here assumed as equal to 1, just an expedient to mimic the Chiapia outcrop, where also the small fractures are strata-bound. The grid size in relation to the estimated fracture's length. In fact, the cell size has to be about equal or larger than the fracture's length. Otherwise, the calculated connectivity index is bound to underestimate the real connectivity. Using a workflow in petrol, the 3 sets of fractures recognized in the envisaged boreholes have been stochastically modeled using the fracture's length and the fracture's intensity P32 as variables to be tuned for reaching, by iterations, the selected mean connectivity value of 2. This sketch summarizes the iteration process. So, based on the few borehole data, we have built a stochastic DFN of a potentially connected fractured reservoir just an initial realized to be tested and tuned along the time according to the new collected geological and dynamic data. These are the histograms of the final values of fractures length and intensity, and the obtained connectivity index. This DFN is composed by 1,262 fractures, about equally divided in the 3 sets assumed as equivalent, and this is the upscaled P32 property. The connectivity of the fractures network is of course affected also by the continuity of the cells with high connectivity index values that results in this specific test quite good. Of course, this initial approach neglects a lot of aspects like the trends or clustering or anisotropy of the fractures network intensity, all aspects to be considered with the collection of additional data. In fact, additional geological data could allow the building of 3D fractures intensity property to drive the stochastic simulations of the DFN. However, this first DFN realization allows to perform some initial sensitivities about the possible impact of a fractured reservoir. In fact, the output of these iterations, fractures, length and intensity, can be utilized to realize, at larger scale, a DFN geometrically connected that is the first issue to be investigated in the building of a fractured model. This initial approach could be calibrated, making some hypotheses about the most suitable analogues. Integrating all the available geological data, a NFN could be selected as the best analog, that is, for this test, the Chiapea pavement outcrop. So, this is the analog for this test. The following easy and fast workflow has been utilized for the building of the deterministic NFN. Digitization on outcrop photos of polygons for all the recognizable fractures. Put in depth of the polygons. Deterministic NFN generation. In this test, the digitization is not made on orthophotos, as it should be, but just on photos taken from the overlying cliff. A reasonable approximation for this kind of exercise. The digitized polygons follow the shape of the fractures, and so the resulting fractures planes are not just linear. For simplicity's sake, the fractures have been assumed as vertical, as observed in this outcrop, although any kind of dip could be described. So, based on the Chiapea outcrop photos, polygons have been digitized very quickly and the relative patches created. To have a more statistically representative samples of fractures, the digitized polygons patterns have been duplicated laterally 4 times. We observe that Set 1 intensity is higher in the fold zone. Set 3 intensity is reducing eastwards. On the right of the fault zone, all the fractures trend is little rotated counterclockwise. These are the parameters: fractures length, intensity, and connectivity index that can be inferred from the deterministic NFN that describes roughly the discontinuities of the Chappia pavement. It is to be noted that the resulting connectivity index is quite low, probably affected by the approximation of the digitized polygons. In fact, despite the large number of observed fractures, the network results quite discontinuous. Based on the characteristics of the so-defined deterministic NFN, assumed as benchmark, we can try to optimize the building of the stochastic DFN. Pragmatically, the main target is the reproduction of the fractures network geometrical connectivity. The tuning process has been performed by iterations in 2 steps. Preliminary analysis of the deterministic NFN by fractures set to define the initial DFN fractures length, FL, and intensity, upscaled P32. Final optimization at model scale of the DFN connectivity, matching the upscaled NFN connectivity index tuning by iterations, fractures length, and intensity. Based on the input inferred from the deterministic NFN, the optimization at model scale of the DFN connectivity is performed tuning the fractures length and intensity. The connectivity properties result quite similar. Despite the good match of the connectivity index, the DFN results quite different from the NFN in terms of number of fractures and P32. Differences that could be partly minimized working on the stochastic simulation parameters. For example, fixing the fractures length and just increasing the fractures intensity to reach the connectivity value target, we could get a DFN characterized by fractures number and intensity more similar to the NFN. However, the pragmatic target is not the replication of the topology of the NFN outcrop, but rather its connectivity that is defined by the presence of links between fractures, whatever are the terminations, X nodes, cross, or Y nodes, abutment. So, the workflow is here summarized. Borehole data collection and analysis, conceptual geological model definition, by integration with all the available data, analog selection, building of a small deterministic natural fractures model according to the selected analog, calibration of the small DFN model focusing on the fractures network connectivity, propagation of the tuned DFN at field scale. The process relies on 2 Petrel workflows. The first one generates deterministic fractures based on the digitized polygons according to the selected analog and the conceptual geological model. The second one realizes the stochastic simulated DFN according to the fractures parameters that lead to the estimated connectivity. To make this approach more effective and faster, could be useful to have a kind of outcrop pavement images database related to different scenarios from which infer fractures network patterns. They could be so utilized, once adapted to the specific context, for the building of small deterministic NFN on which calibrate the DFN. Of course, different areas of the field could call for different analog and calibrating deterministic NFNs. However, we must remember that connectivity is just one piece of the puzzle. In fact, in the process of building fractures models, the following steps, that is the petrophysical characterization of the fractures network, is definitely the most critical and important issue to be faced. Here, a short list of papers relevant to the topics briefly discussed in this presentation. So long.